Continuing on with chapter 10, we will now look at section 10.3 where sigma is unknown. So we will still look at hypothesis tests for the population mean mu, but now we will assume that sigma is unknown. And as we have mentioned several times, it is highly unlikely in practice that the population standard deviation would be known. Recall that when sigma is known, we use the z-distribution, along with table B to calculate the test statistic and determine the decision rule for the rejection region. In this case, the test statistic is given by this formula. In this section, we will now assume that sigma is unknown and use the student's t-distribution, along with table C, to calculate the test statistic and determine the decision rule for the rejection region. In this case, the test statistic is given by the following formula. And again, this is our second formula in the left column on our exam 5 formula sheet. Notice not much changes except for the fact that sigma becomes S, and doing so changes our Z to a T. Let's look at an example. Determine which distribution to use for the test statistic. A computer program designer has developed an online questionnaire that she believes will take a mean time of 15 minutes to complete. Suppose that she samples 35 volunteers and finds that the mean time to complete the questionnaire is 14.0 minutes. Determine if there is sufficient evidence to conclude that the mean completion time for the online questionnaire differs from its intended duration. Use a 0.05 level of significance and assume that the population standard deviation is known to be 2.5 minutes. In this problem, we have the statement, assume that the population standard deviation is known to be 2.5 minutes. This tells us that sigma is 2.5. When we look at our exam 5 formula sheet, the only formula that allows us to plug in the value of sigma comes in the form of a z-value, right? It's our first formula in the left column of our exam 5 formula sheet. So in this case, we would use the z-distribution. Looking at the next example, a manufacturer is responsible for making barrels used to store crude oil, which are designed to hold exactly 55 gallons of oil. As part of a routine quality check, a factory manager randomly tests 27 barrels off the assembly line and finds that their mean is 54.7 gallons with a standard deviation of 0.8 gallons. Can the manager say with 99% confidence that the requirements are being met? Assume that the population distribution is approximately normal. Now, in this problem, we have the statement, a factory manager randomly tests 27 barrels and finds a standard deviation of 0.8 gallons. Now, I've skipped some wording between here, but this is the idea in that sentence. This tells us that the standard deviation has been calculated from the sample. When we look at our exam 5 formula sheet, the only formula that allows us to plug in the value of S, remember, S is our sample standard deviation, comes in the form of a t-value, right? And it's this formula. So in this case, we would use the student's t-distribution, or our table C. Note, just a fine print here, note that the statement, assume that the population distribution is approximately normal, is given since the sample size is less than 30. So to be able to use the student's t-distribution, we need to be sure that the population distribution is normal or approximately normal. So this is just a fine print of the problem, but it has nothing to do with which distribution we use. Recall from section 10.2 that there are 3 types of hypothesis tests, right? We have a left-tailed test, a right-tailed test, and a two-tailed test. And all of these are determined by the symbol given in our alternative hypothesis, our HA. These 3, right? So, and we create the following decision rules. So we have the following decision rules. Our left-tailed test, remember that we block off the area alpha to the left. Our right-tailed test, we block off our area to the right, And our two-tailed test, we block off half of the area to the right and the left. And our goal when deciding is to find our boundary value and compare it to our test statistic. So when we're drawing our conclusion, when sigma is unknown, we will reject the null hypothesis H naught if t is less than or equal to negative t alpha for a left-tailed test, t is greater than or equal to t alpha for a right-tailed test, and the absolute value of t is greater than or equal to t alpha over 2 for a two-tailed test. And again, this is how we mathematically write the statement that our test statistic falls within the rejection region. So this is how we mathematically write each visual picture given in the previous slide. And my recommendation is to just memorize these. These are exactly what we saw in section 10.2, except we're just replacing our z values with t values because sigma is unknown. So let's recall the four-step process to successfully complete a hypothesis test. Step 1, state H naught and HA. Step 2, compute the value of the test statistic. Step 3, determine the rejection region, or what we call the decision rule. And step 4, conclude. Let's look at an example. Nurses in a large teaching hospital have complained for many years that they are overworked and understaffed. The consensus among the nursing staff is that the mean number of patients per nurse each shift is 8.0. The hospital administrators claim that the mean is lower than 8.0. To prove their point to the nursing staff, the administrators gather information from a simple random sample of 19 nurses' shifts. The mean is 7.5 patients per nurse with a standard deviation of 1.1 patients per nurse. Test the administrator's claim using alpha equals 0.025 and assume that the number of patients per nurse has a normal distribution. We begin with step 1, stating the hypotheses. So our claim is that the mean is less than 8.0, right? The average number of patients per nurse is less than 8.0. And remember our null hypothesis, we simply replace the symbol with equality. Now, to compute the value of the test statistic, this is our step 2, we need to pull out and label all numeric values given in the problem. So in the problem, we have a simple random sample of 19. Our sample mean is 7.5, and notice that our sample standard deviation is given as 1.1. There is no statement in this problem that says assume the population standard deviation. So this is a scenario where the sample standard deviation is given. This problem gives us the sample standard deviation. So again, sigma is unknown. And also remember that we use the value given in our null hypothesis, mu equals 8, for our formula. So plugging everything into our t formula, x bar, 7.5, our mu was given to be 8.0, our s, 1.1, and our n, 19, we get t is approximately negative 1.981. Now remember that t values, unlike z values, are rounded to 3 decimal places. To create our decision rule, or our rejection region, this is our step 3, we first notice that alpha given in the problem is 0.025. We also need a degrees of freedom. Remember that t values need a degrees of freedom to use table C. Now the formula on your exam 5 formula sheet tells us that t is this, and right next to it, it says, remember, the degrees of freedom is n minus 1. And we saw this from chapter 8. So our n was 19. 19 minus 1 gives us 18. Using table C, we use the area in one tail. And why do we use the area in one tail? If we go back to our HA, our alternative hypothesis, we see the less than symbol. Which way does the arrow point? it points to the left. So this is a left-tailed test, which is a one-tailed test. So we use the area and one-tail, and we see that t is 2.101. Remember, we line up our row, degrees of freedom 18, with our column, area and one-tail, 0.025. We line those up, and we get 2.101. Now, we have to remember that it's a left-tailed test. So our decision rule is that we will reject if t, our test statistic, remember we're using t values, is less than or equal to negative this value, because we want the boundary value on the left side. Left side are always negative values, right? So we make it negative 2.101, right? Here's a picture, right? Here's our boundary value, negative 2.101, and we're blocking off an area of 0.025. So now we conclude, this is our step 4. So we compare our step 2, our test statistic, and our step 3, our decision rule. Now our test statistic was negative 1.981. The question is, does this satisfy our decision rule? Notice that negative 1.981 is not less than or equal to negative 2.101. So we're not in this rejection region, this shaded region. So in this case, we failed to reject H naught. Again, if we want to interpret this problem, we can interpret the conclusion of failing to reject the null hypothesis to mean that the evidence collected is not strong enough at the 0.025 level of significance to reject the null hypothesis in favor of the administrator's claim that the mean number of patients per nurse is less than 8.0. Okay. Let's look at another example. So the meat packing department of a grocery store chain packs ground beef in 2-pound portions. Supervisors are concerned that their machine is no longer packaging the beef to the required specifications. To test the claim that the mean weight of ground beef portions is not 2.00 pounds, the supervisors calculate the mean weight for a simple random sample of 20 packages of beef. The sample mean is 2.10 pounds with a standard deviation of 0.33 pounds. Is there sufficient evidence at the 0.01 level of significance to show that the machine is not working properly? Again, assume that the weights are normally distributed. Okay. Now, again, we've seen kind of the trend here, right? These problems are becoming longer, and there's more words involved. So these problems require a good reading comprehension from each of you students, right? So not only do we need to read the problem once, we want to read it again, and as we're reading it again, we want to not only ask ourselves, what is this problem asking, but we want to start pulling out our numeric values and correctly labeling them. Labeling all of these numeric values will help you solve this problem. Okay, so again, step 1, we need to state the hypotheses. Now, what are we asking ourselves? Is there sufficient evidence to show that the machine is not working properly? Okay, so what does it mean to not be working properly? So we want to test the claim that the mean weight of ground beef portions is not 2 pounds. How do we say that mathematically? The mean weight is not equals 2 pounds. And again, our H naught is just replace the symbol with equality. Now, to compute the value of the test statistic, we need to pull out and label all numeric values. So in this case, our sample size was 20. Our sample mean was 2.10 pounds. And again, notice that we're given the sample standard deviation in this problem, 0.33. There's no statement in this problem that says assume the population standard deviation, okay? Now, finally, we need to note that in our formula, we need a value for mu. We use our H naught. So calculating our t value, we get approximately 1.355. And again, we want to round to 3 decimals since it's a t-value. Now, to create our decision rule for a rejection region, we first notice that alpha, given in the problem, is 0.01. We also needed degrees of freedom. So right next to our formula on our exam 5 formula sheet, remember it says degrees of freedom is n minus 1. So our sample size in this problem was 20. 20 minus 1 is 19. Using table C, we use the area in two tails, and this is because we have the symbol not equals. Not equals represents a two-tailed test. And lining those up, degrees of freedom 19, area in two tails 0.01, we get 2.861. So our decision rule, our rule for our rejection region, is the absolute value of t is greater than or equal to 2.861. This is what we use to decide if we reject H0. Now, since our test statistic in step 2 was 1.355, we see that 1.355 is not bigger than 2.861. So again, we failed to reject, and we can see the picture here. We have our boundary value of 2.861, our boundary value of negative 2.861 because it's a two-tailed test. And notice that 1.355 is not in the either of the shaded regions. We can interpret failing to reject the null hypothesis to mean that the evidence collected is not strong enough at the 0.01 level of significance to say that the machine is working improperly. As always, especially in this chapter, these problems become much more in-depth. If you're struggling, please post on our Module 10 discussion board or send me an email at my UNA email.